On the night of August 30th, 2019, something crosses the threshold of Earth's orbital plane. It moves through the constellation Cassiopeia, silent and unannounced. Though it has been travelling for perhaps millions of years, no fanfare accompanies its arrival. No atmospheric friction slows its passage. It simply exists, suddenly visible, a smudge of reflected sunlight against the stellar background, carrying ice and carbon and complex molecules from a place that has no name. The object measures perhaps 1 kilometre across its longest axis, small enough to escape notice for weeks, large enough to hold within its frozen matrix the chemical fingerprints of another world's formation. It glows faintly as the sun's radiation begins to warm its ancient surface, releasing gases that have been locked in darkness since before Earth's continents took their current shapes. The coma that forms around it, that hazy envelope of sublimating ice, spreads outward in the solar wind, a temporary atmosphere for something that will never know a sky. Astronomers will later calculate that it entered the solar system from the direction of the constellation Cassiopeia at a velocity of roughly 32 kilometers per second relative to the Sun. This speed carries significance. Objects bound to the Sun, no matter how distant their orbits, move according to Kepler's mathematics, their velocities tied to solar gravity's embrace. But this object moves differently. Its trajectory bends only slightly as it passes through the Sun's gravitational field, a hyperbola rather than an ellipse, the geometric signature of something unbound. It will not return. It is only passing through. The light that reflects from its surface took 8 minutes to travel from the Sun. The light from the star system where it formed, wherever that might be, has been travelling for years, decades, perhaps centuries, depending on which stellar neighbourhood gave it birth. Time collapses into this single moving point, this wanderer that connects two stellar systems through its solitary journey. A messenger carrying news that no one sent and that arrives without translation. In the nights following its initial detection, the object brightens slightly as it moves closer to the Sun. This brightening follows predictable patterns, the mathematics of sublimation and solar distance. Water ice transitions directly to vapour at the boundary between solid and gas, skipping the liquid phase entirely in the vacuum. Carbon monoxide follows, and other volatiles trapped in the comet's structure since its formation. Each molecule that escapes carries away a tiny fraction of the object's mass, eroding it molecule by molecule, a process so slow it barely registers except through the most sensitive instruments. The comet's designation will change twice in the weeks following discovery. First, it receives a provisional designation based on the date of detection. Then, as observations accumulate and its interstellar origin becomes undeniable, it receives the prefix 2I, the second interstellar object ever confirmed. The first, Oumuamua, passed through 2 years earlier, mysterious and silent, offering no spectroscopic data, no cometary activity, only questions. This second visitor behaves differently. It glows, it outgasses, it acts in almost every measurable way, like the comets that have always belonged to the Sun's family. Almost. Only took 4.5 billion years for Earth's instruments to become sensitive enough to detect such visitors. Only required the construction of telescopes that can measure the spectrum of something 1 billion times fainter than the human eye can perceive. Only needed the development of orbital mechanics precise enough to distinguish between merely distant and actually alien. The universe waited patiently. The Discovery images show nothing dramatic, a faint streak against background stars, a slight elongation indicating motion across the detector. The object reveals itself through mathematics rather than spectacle, through the subtle wrongness of its trajectory when compared to the thousands of known comets and asteroids whose paths crisscross the inner solar system. Computers flag it, humans investigate, the numbers accumulate into certainty. Somewhere in the galaxy, perhaps 100 light-years away, perhaps 300, a planetary system continues its slow evolution. Planets orbit a star that might be redder than the Sun, or bluer, or perhaps almost identical in spectral type. Dust continues to spiral inward toward that star. Comets still populate its outer reaches, frozen and dark, waiting for gravitational perturbations that might never come. One comet from that system now moves through ours. Its chemistry slightly different, its isotopic ratios carrying the signature of formation conditions that varied in small but measurable ways from the conditions that prevailed here. The comet crosses the ecliptic plane at an angle of approximately 40 degrees, cutting through the flat disk where Earth and the other planets orbit. Its path will carry it to within 2 astronomical units of the Sun, twice Earth's distance, before gravity slings it back outward, adding solar velocity to its existing motion, accelerating it into the darkness beyond. The Sun barely notices. 4.5 billion years of gravitational dominance, and this small frozen visitor passes through like starlight through glass, refracted but not captured. In observatories across Earth's surface, telescopes begin to track the object. In Hawaii, on mountaintops in Chile, in the desert regions where atmosphere thins to transparency, instruments swing toward Cassiopeia. The observations must begin quickly. The comet will remain bright enough for detailed study for only a few months. After that, it will fade beyond the reach of even the most powerful telescopes, carrying its chemistry back into the dark, leaving behind only the data that human instruments managed to capture during its brief passage through observability. The sky holds the object steady, neither accelerating it nor slowing it beyond what gravity requires. The comet moves according to laws that operate everywhere, in every galaxy, making no distinction between familiar and foreign. Newton's mathematics describe it perfectly. Einstein's corrections apply equally. The universe uses the same physics everywhere, which is either deeply comforting or profoundly unsettling, depending on how one thinks about home. The trajectory reveals itself through successive observations, each measurement refining the orbital elements, narrowing the uncertainty. Astronomers calculate eccentricity first, the parameter that describes how much an orbit deviates from a perfect circle. For objects bound to the Sun, eccentricity ranges from 0 to just under 1. Circular orbits score 0. Highly elliptical comet orbits approach but never quite reach 1. This object's eccentricity exceeds 3. The mathematics allow no ambiguity. No object with an eccentricity greater than 1 can remain bound to the Sun. It arrives from interstellar space and will return there, following a hyperbolic path that opens ever wider as distance from the Sun increases. The orbital inclination comes next, the angle between the object's path and Earth's orbital plane. 44 degrees, steeply inclined compared to most solar system bodies, but not impossibly so. Some long-period comets from the Oort cloud arrive at similar angles, dropped inward by stellar perturbations from random directions. But those comets slow as they approach the Sun, their velocities bound by gravitational potential. This object maintains its speed. The numbers refuse to fit cometary patterns no matter how the calculations are adjusted. Perihelion distance settles at approximately 2 astronomical units, scheduled for early December 2019. Close enough for solar heating to drive vigorous outgassing, far enough to avoid the extreme temperatures that would cause catastrophic fragmentation. The comet will never approach Earth's orbit. It will never come closer than Mars typically orbits. It remains, even at its nearest point, safely removed from the inner solar system's chaos, threading a path through the space between Mars and Jupiter, where the asteroid belt maintains its patient circulation. The argument of perihelion and the longitude of ascending node parameters that specify exactly where and when the comet crosses certain reference planes complete the orbital solution. 6 numbers fully describe the comet's path through 3-dimensional space. 6 parameters that, when computed backward in time, trace the object's route through the solar system, through the heliopause where the solar wind surrenders to interstellar medium, through the decades or centuries of travel in the dark between stars, all the way back to some moment of ejection from a system that remains unidentified. Only required humans to invent calculus, orbital mechanics, and telescopic observation to perform these calculations. Only took 4 centuries of astronomical tradition. Building on Kepler's laws and Newton's gravity and Einstein's refinements, only needed the patient accumulation of observation after observation, night after night, as the comet moved against the background stars with motion too slow for human eyes but perfectly captured by electronic detectors. The universe makes no concessions to convenience. The uncertainty shrinks with each observation. Early calculations show possible trajectories forming a cone of probability through space. Within a week, the cone narrows. Within 2 weeks, the hyperbolic nature becomes undeniable. Within a month, the orbital elements are known to within fractions of a percent, sufficient to predict the comet's position years into the future or to reconstruct its path decades into the past. The mathematics compile a history that no one witnessed and a future that no telescope will observe. Some astronomers attempt to trace the trajectory back to specific star systems. The comet enters the solar system from approximately the direction of Cassiopeia, but approximately contains too much uncertainty. Space is vast and nearly empty. The comet could have originated from any of hundreds of stars in that general direction, or from thousands of stars if its journey took long enough for stellar proper motions to scramble the geometry. Each star moves through the galaxy on its own trajectory, and over timescales of millions of years, stellar neighborhoods dissolve and reform in new configurations. The calculations run backward through galactic rotation, accounting for the sun's motion around the Milky Way's center, for the comet's likely velocity and the local standard of rest, for the gravitational influence of nearby massive structures. No star system produces a perfect match. Several show promising alignment, but with margins of error too large for certainty. The comet's origin remains statistically probable, but specifically unidentifiable, like a letter delivered without a return address. Its source narrowed to a continent but not a city, a region but not a home. This ambiguity frustrates attempts at classification. Astronomers prefer clean categories. Solar system comets get numbered designations. Asteroid families trace back to specific collision events. Even meteor streams identify with parent bodies. But this visitor arrives from somewhere, carrying chemistry from somewhere, and somewhere must suffice as an address. The precision that characterizes modern astronomy falters in the face of interstellar distances and galactic timescales. The comet's velocity relative to the local standard of rest, the reference frame defined by the average motion of nearby stars, measures approximately 32 kilometers per second. This falls within the expected range for objects moving through the local interstellar medium. Not especially fast, not remarkably slow, just typical, which itself carries meaning. The comet was not ejected at extreme velocity by some catastrophic event. It left its home system through processes that impart moderate speeds, the kind of speeds that planetary migration or stellar encounters routinely generate. Imagine ejection mechanics, a planetary system still forming, gas giants migrating inward through the protoplanetary disk, their gravity flinging smaller bodies outward like stones from a sling, or perhaps stellar encounters, 2 stars passing within light weeks of each other, their combined gravitational fields perturbing Oort cloud-equivalent objects, sending some into the parent star and others out into the galaxy. These processes operate in every planetary system, suggesting that interstellar space contains vast populations of ejected comets, asteroids, and planetesimals, all moving through the dark between stars, occasionally passing through other systems by chance. The statistics become overwhelming when calculated properly. The galaxy contains roughly 100 billion stars. If each star system produces even a modest number of ejected objects during its formation and evolution, the total population of interstellar wanderers reaches truly astronomical numbers. Most remain forever dark and frozen, never passing close enough to a star to become active or observable. A tiny fraction transit through stellar systems where technological civilizations have developed instruments sensitive enough to detect them. An even tinier fraction of that fraction get discovered before fading back into darkness. Earth's observatories detect one such object in 2017, another in 2019. 2 confirmed interstellar visitors in 2 years. Statistical models suggest this sample badly underrepresents the true population. For every interstellar object detected, hundreds or thousands pass through unnoticed, too small, too dark, or arriving from angles that keep them out of surveyed regions of sky. The solar system swims through a sea of ejected debris from other stellar systems, most of it remaining perpetually invisible, known only through inference and statistical prediction. Only took the detection of 2 objects to revolutionize understanding of how common such transits might be. Only required direct observation to confirm what theory had long suggested. Only needed instruments capable of distinguishing faint moving objects from the billions of background stars to reveal that Earth's system sits at a crossroads of galactic traffic, with visitors arriving constantly, most passing through without announcement. The universe operates at scales that make human awareness seem like a recent and temporary phenomenon. The comet continues moving, indifferent to the attention it receives, to the calculations tracing its past, to the instruments measuring its present. It follows its hyperbolic path with the inevitability of mathematics, curving through the inner solar system according to gravity's requirements, soon to reach perihelion and begin its outward journey. The observations accumulate. The orbital solution refines. The mystery of its origin persists. Gennady Borisov operates the Margot Observatory on Crimea's southern coast, near the city of Noshny. The telescope he uses is homemade, a 0.65-meter reflector that he designed and assembled himself, optimizing it for the discovery of comets and asteroids. On the night of August 30, 2019, he images a region of sky in Cassiopeia, capturing exposures that reveal a faint elongated smudge among the stellar background. The object shows motion. He notes its position, measures its brightness, and continues observing. Amateur astronomers have discovered comets for centuries, following traditional patterns of patient sky surveys and careful record-keeping. Borisov follows this tradition, though his equipment surpasses what amateur might suggest to casual observers. His telescope rivals instruments at professional facilities from earlier decades. His techniques incorporate modern CCD imaging and digital processing. His dedication manifests in nightly observations when weather permits, scanning regions of sky where new comets might appear, comparing current images to previous nights, looking for motion that indicates something new. The initial observations show nothing extraordinary. A comet, probably. Faint but active, with a visible coma suggesting outgassing. Borisov reports the discovery through the Minor Planet Center, the international clearinghouse for observations of small solar system bodies. His report includes positions, times, brightness estimates, and notes about the object's appearance. The Minor Planet Center assigns a provisional designation and adds the object to its watch list for follow-up observations. Other observers begin tracking the comet within days. Telescopes in Hawaii, Arizona, and Chile acquire confirmation images. The observations accumulate in the Minor Planet Center's database, each new position measurement refining the orbital calculation. Within a week, something becomes apparent. The orbit shows unusual characteristics. The eccentricity keeps rising with each new calculation, pushing beyond values that would indicate merely a long-period comet. By September 11th, the orbital solution suggests the unthinkable. This might be the second interstellar object ever detected. Only required one person checking the right patch of sky at the right time to make the discovery. Only needed clear skies over Crimea on that particular night in August. Only took decades of Borisov's patient observation, night after night, building expertise and refining techniques to recognize something unusual in the digital images. The universe rewards persistence without guaranteeing success. Borisov himself remains characteristically modest about the discovery. In interviews, he emphasizes the routine nature of his observing program, systematic sky surveys that eventually reveal anything moving through the surveyed regions. He built his telescope for comet discovery. He discovered a comet. That the comet originated beyond the solar system makes it scientifically exceptional, but does not change the fundamental process of discovery, careful observation, accurate measurement, prompt reporting. The observatory sits at latitude 44 degrees north, positioned to survey northern celestial regions throughout the year. Crimea's climate provides reasonably stable observing conditions, with clear nights frequent enough to maintain systematic surveys. The site lacks the pristine darkness of mountaintop observatories in Chile or Hawaii. But Borisov's techniques compensate, using sensitive detectors and image processing to extract signals from light-polluted skies. The comet's discovery required adequate but not exceptional conditions, the kind of conditions available to dedicated observers in many locations. The telescope's mount tracks the sky's rotation, compensating for Earth's spin to keep celestial objects stationary in the field of view during exposures. This tracking allows longer exposures that accumulate more light from faint objects. Borisov's exposures typically last several minutes, long enough for comets to reveal themselves through their slight motion against background stars. Comparing exposures taken hours or nights apart shows which objects moved and how fast, distinguishing solar system bodies from distant stars. The digital images contain hundreds of thousands of pixels, each recording the light that fell on that detector element during the exposure. Software processes these images, identifying objects, measuring their positions and brightnesses, comparing them to catalogues of known stars and known solar system bodies. Objects that appear in the images but not in the catalogues become candidates for follow-up. Most candidates resolve into known objects once orbital calculations connect them to previous detections. Occasionally, something genuinely new appears. Discovery images capture only a fraction of the comet's light. Most of the sunlight striking the comet's nucleus reflects into space in directions that miss Earth entirely. The tiny portion that reflects toward Earth then travels 1.5 astronomical units, the distance between Earth and the comet, a discovery spreading according to the inverse square law, arriving so diffused that only the most sensitive detectors can capture it. That humans can detect such objects at all represents an impressive technical achievement, the culmination of centuries of optical refinement and decades of electronic detector development. The comet's appearance in the discovery images shows a condensed central region surrounded by a more diffuse coma. This morphology immediately suggests cometary activity, a nucleus releasing gas and dust that scatters sunlight. Asteroids appear as point sources, star-like even in detailed images. Comets show extended envelopes, the signatures of sublimation. Borisov recognizes this morphology instantly, the pattern familiar from hundreds of previous comet observations, though none of those previous comets arrived from interstellar space. Only after other observers confirm the discovery and additional orbital calculations refine the trajectory did the comet's interstellar nature become certain. Only after the minor planet's center circulated the unusual orbital elements did the broader astronomical community recognize the significance. Only after spectroscopic observations revealed the comet's composition did its full importance emerge. Borisov discovered the object, but the discovery's meaning required the collaborative work of the global astronomical community, each observer adding data, each calculation narrowing uncertainty. The comet receives its final designation in late September. Borisov, the second interstellar object, named for its discoverer. The I stands for interstellar, a new category in astronomical nomenclature created specifically for Oumuamua 2 years earlier. Before 2017, no designation system existed for interstellar objects because none had been definitively detected. Now the system accommodates them, preparing for future discoveries that theory suggests should arrive regularly as survey telescopes improve in sensitivity and sky coverage. Borisov continues his observing program, scanning new regions of sky each clear night. searching for the next comet or asteroid that reveals itself through motion against the background stars. One discovery does not complete the work. The sky remains vast and mostly unsurveyed. New objects appear constantly, some ordinary, some exceptional, all contributing to the accumulated catalogue of small bodies moving through the solar system and sometimes through the space beyond. The telescope sits quiet during daylight, its optics protected, its mount idle, waiting for darkness to return. At night it swings into motion again, tracking across constellations, capturing images, recording positions. The routine continues, methodical and patient, producing data that occasionally transforms understanding but more often simply documents the expected behaviour of expected objects. Both outcomes matter. Both contribute to knowledge. Spectroscopy reveals what chemistry the comet carries. Light from the sun strikes the comet's nucleus and the gases surrounding it, exciting molecules into higher energy states. As these molecules relax back to lower energies, they emit light at specific wavelengths determined by quantum mechanics, each molecule producing a unique pattern of emission lines, like a fingerprint written in photons. Telescopes equipped with spectrographs spread this light into its component wavelengths, revealing which molecules populate the coma. Water appears immediately in the spectra, identified by the characteristic emission lines of hydroxyl radicals, OH molecules, produced when ultraviolet sunlight breaks apart H2O. This comes as no surprise. Water ice dominates the composition of most solar system comets, typically comprising 80% or more of the volatile material. Comets formed in the cold outer regions of the protoplanetary disk, where water could condense into ice, accumulating into larger bodies through gentle collisions. That 2I Borisov contains water suggests it also formed in a cold environment, distant from its parent star. Carbon monoxide shows strongly in the spectra, more abundant relative to water than in typical solar system comets. The CO to H2O ratio measures approximately 55%, meaning for every 2 water molecules in the coma, roughly 1 carbon monoxide molecule accompanies them. This ratio exceeds what most solar system comets display. Only the most pristine comets from the Oort cloud, those that have never passed close to the Sun, show comparable carbon monoxide enrichment. The high CO abundance indicates formation in exceptionally cold conditions, where carbon monoxide ice could remain stable. Cyanogen appears as well, identified by the CN emission bands in the violet region of the spectrum. Cyanogen, a radical consisting of 1 carbon and 1 nitrogen atom, likely originates from more complex parent molecules in the nucleus that break down under solar ultraviolet radiation. Its presence indicates the comet contains nitrogen-bearing compounds, organic molecules that may include hydrogen cyanide or more complex cyanides. These molecules trace back to the chemistry of the protoplanetary disk where the comet formed, to reactions between carbon, nitrogen, and hydrogen in regions shielded from starlight. Only required the comet to approach within 2 astronomical units for sufficient solar heating to drive out gassing at detectable levels. Only needed observatories with sensitive spectrographs and large collecting areas to gather enough photons for spectral analysis. Only took computational processing to identify emission lines against the background continuum and match them to known molecular transitions. The universe compresses billions of years of chemical history into patterns of light that instruments can decode in minutes. The spectroscopic data allow estimates of production rates, how many molecules per second the comet releases as its nucleus sublimates. Water production peaks at approximately 20 kilograms per second near perihelion. Carbon monoxide escapes at roughly 10 kilograms per second. These rates sound substantial, but represent tiny fractions of the comet's total mass. At these production rates, the comet could sustain activity for millions of years before exhausting its volatile inventory, though in practice it will fade back into the cold of interstellar space long before depletion occurs. Temperature calculations suggest the nuclear surface reaches perhaps 180 to 200 Kelvin near perihelion cold by terrestrial standards, but warm enough for water ice to sublimate in vacuum. carbon monoxide, more volatile than water, begins outgassing at even lower temperatures, perhaps as far out as 3 or 4 astronomical units from the Sun. The comet likely started showing activity months before discovery, developing its coma gradually as solar heating increased during inward passage. Some molecules remain undetected or ambiguous in the spectra. Ammonia, common in solar system comets, shows weak or absent signatures. Methane, another volatile species expected in primitive ices, produces no clear detection. These absences might reflect genuine compositional differences, or they might simply indicate that observation conditions and spectral sensitivity proved insufficient to detect these species at their actual abundances. Spectroscopy reveals presence with confidence but struggles with definitive absence. The isotopic ratios remain largely unmeasurable with available instruments. Isotopes of the same element behave nearly identically chemically, but differ in nuclear mass, producing subtle shifts in molecular emission wavelengths. Measuring these shifts requires extremely high spectral resolution and signal-to-noise ratios that even large telescopes struggle to achieve for faint comets. A few attempts to measure deuterium to hydrogen ratios in the water vapour suggest values consistent with solar system comets, but uncertainties remain large. The isotopic fingerprints that could definitively reveal formation conditions remain tantalizingly just beyond current measurement capabilities. The dust component reveals itself through reflected sunlight continuous spectrum without emission lines, showing the reddish colour characteristic of many solar system comets. This colour comes from complex organic compounds, long-chain carbon molecules called tholins that form through radiation processing of simpler ices over geological timescales. The presence of reddish dust suggests the comet's surface experienced radiation exposure, perhaps during its journey through interstellar space, or perhaps during an earlier phase while still in its birth system. Dust production rates estimated from brightness and colour measurements suggest the comet releases comparable amounts of dust and gas, a dust-to-gas ratio near unity. This ratio resembles typical solar system comets, where sublimating ice carries entrained dust grains out of the nucleus. Gas drag lifts particles that gravity alone cannot hold, creating the dust coma that scatters sunlight and makes the comet visible. The similar dust-to-gas ratio suggests similar nucleus structures, ice matrices with embedded dust, perhaps with similar porosity and strength characteristics. Only the comet itself knows the complete inventory of molecules frozen in its nucleus. Only direct sampling could reveal the full compositional complexity, the trace species present at parts per million levels, the isotopic variations that record formation temperature and stellar radiation environment. But direct sampling requires spacecraft missions years in the planning and execution, and 2I Borisov moves on a trajectory that makes interception nearly impossible with current propulsion technology. The comet will carry most of its secrets back into interstellar space, revealing only what remote spectroscopy can extract from reflected and emitted light. The molecules detected water, carbon monoxide, cyanogen paint a portrait of cold chemistry, of ices condensing in the outer reaches of a protoplanetary disk, of organic synthesis occurring in darkness and cold, of processes that appear universal across different stellar systems. The similarities to solar system comets suggest that planet formation follows similar pathways everywhere, that the physics and chemistry of condensing gas clouds and orbiting planetesimals operate identically whether around this sun or some distant star in the direction of Cassiopeia. The spectrum shows what the comet carries but not where it formed, not which star's light first warmed its surface, not what planets orbit in the system it left behind. The chemistry constrains formation conditions cold, distant from the star, rich in volatiles, but thousands of stellar systems could produce such conditions. The molecules travel across light years but arrive without metadata, without tags identifying their origin, without context beyond what quantum mechanics permits them to reveal through emission lines. The carbon monoxide abundance stands out most prominently in comparative analyses. Solar system comets show wide variation in their CO-to-water ratios, ranging from barely detectable traces up to perhaps 30% in the most pristine Oort cloud objects. The ratio of 55% observed in 2I Borisov exceeds nearly all solar system values, placing it at the extreme end of the distribution, or perhaps beyond it entirely. This elevated carbon monoxide content carries implications for where and how the comet formed. Carbon monoxide ice remains stable only at low temperatures, sublimating away at temperatures above approximately 25 Kelvin. In the Sun's protoplanetary disk, this temperature boundary occurred somewhere beyond Neptune's orbit, in the region where the Kuiper belt eventually formed. Closer to the Sun, temperatures rose high enough that carbon monoxide could not condense into solid ice, remaining gaseous and gradually escaping from the inner solar system. Objects forming in these warmer regions incorporated little carbon monoxide into their structure. Jupiter likely formed in a region where temperatures hovered around 30 to 40 Kelvin, warm enough that carbon monoxide existed primarily as gas rather than ice. The giant planet's atmosphere reflects this formation environment relatively depleted in carbon monoxide compared to the Sun's overall composition. Objects forming in Jupiter's vicinity inherited this depletion. Most solar system comets, even those now residing in the distant Oort cloud, trace their origins to the Jupiter-Saturn region and carry the chemical signature of formation in that moderately cold environment. The high carbon monoxide ratio in 2I Borisov suggests formation in conditions colder than Jupiter's birthplace. Perhaps the comet formed beyond its system's ice giants, in a region analogous to the Kuiper belt but colder still, or perhaps its parent star was cooler than the Sun, a red dwarf or orange dwarf that provided less heating, pushing the snow lines and ice lines farther inward and creating colder conditions at equivalent orbital distances. The chemistry constrains temperature, but cannot uniquely determine distance or stellar properties, only require detailed spectroscopic comparison across dozens of solar system comets to establish the baseline distribution of carbon monoxide abundances. Only needed careful measurement of 2I Borisov's spectrum to place it within or beyond that distribution. Only took theoretical models of protoplanetary disk chemistry to interpret what the elevated carbon monoxide abundance implies about formation conditions. The universe permits inference but rarely provides certainty. Alternative explanations exist. Perhaps the comet formed at typical distances but in an unusually cold protoplanetary disk, one where the parent star was still heavily obscured by infalling material, keeping temperatures lower than expected. Or perhaps the comet spent extended time in interstellar space before entering the solar system, cold enough that carbon monoxide ice accumulated on its surface from the tenuous gas of the interstellar medium. This seems unlikely. The interstellar medium contains too little material for significant accumulation, but cannot be ruled out definitively. The nitrogen chemistry remains less well constrained. Cyanogen emission indicates nitrogen-bearing molecules, but the parent species remain ambiguous. Nitrogen in protoplanetary disks exists primarily as molecular nitrogen N2, which is chemically inert and difficult to observe. In cold regions, nitrogen can incorporate into ammonia ice or various organic molecules. The CN radicals observed in 2I Borisov's coma likely originate from hydrogen cyanide or similar cyanides in the nucleus, but determining the exact parent molecules requires more detailed observations than the comet's brief passage permitted. The oxygen isotope ratios, if they could be measured precisely, would reveal even more about formation conditions. Oxygen has 3 stable isotopes, oxygen-16, oxygen-17 and oxygen-18, with relative abundances that vary depending on temperature during water formation and the specific chemical pathways involved. Solar system objects show correlated patterns in oxygen isotopes, reflecting the history of dust and gas mixing in the Sun's protoplanetary disk. A different stellar system might show different patterns, providing a chemical signature as distinctive as a fingerprint, but measuring isotope ratios requires resolving extremely small wavelength differences in molecular emission lines, shifts of perhaps a few tenths of a nanometer, and detecting these shifts in spectra from an object 1.5 astronomical units away, moving at 32 kilometers per second, with a signal-to-noise ratio that barely permits identification of the emission lines themselves. The measurements approach the limits of what current instruments can achieve. The data exist in the observations, encoded in photon distributions across detector pixels, but extracting meaningful isotopic ratios from noisy spectra remains beyond reliable interpretation. The comet's chemistry suggests universality more than uniqueness. Water, carbon monoxide, cyanogen, organic dust. All these components appear in solar system comets, varying in relative abundance but not in fundamental presence. The comet carries familiar molecules in unfamiliar ratios, hinting at different formation conditions but not radically alien chemistry. The same elements combine in the same ways whether in this solar system or in some distant protoplanetary disk, governed by the same quantum mechanics, the same thermodynamics, the same reaction kinetics. This familiarity carries profound implications. It suggests that the chemistry leading to planet formation operates identically across different stellar environments. It implies that the molecular building blocks available in other planetary systems match those that were available here, that the potential for chemical complexity and perhaps biological chemistry exists wherever planets form. The comet demonstrates through its composition that Earth's chemistry, while local in origin, follows universal principles. Some mysteries persist in the spectroscopic data. Certain emission features appear in the spectra without clear identification, wavelengths that match no known molecular transition, or that might arise from multiple overlapping species. These features could represent rare molecules present in small quantities, or complex organic species not yet fully characterized in laboratory studies, or simply instrumental artifacts masquerading as real signals. Spectroscopy excels at identifying abundant, well-studied molecules, but struggles with unusual or unexpected species. The production rates vary with solar distance, following patterns consistent with sublimation physics. As the comet approached perihelion, water production increased steadily, driven by rising surface temperatures. Carbon monoxide, more volatile, increased earlier and more gradually, driven by subsurface sublimation even when surface ice remained too cold for water to escape. These patterns match theoretical expectations, providing confidence that the spectroscopic interpretations reflect real molecular abundances rather than observational artifacts. Only the briefest window existed for these measurements. The comet remained bright enough for spectroscopy for perhaps 3 months near its closest approach to the Sun. Before that window it was too faint, the emission lines too weak against the noise. After that window it faded rapidly as it moved outward, the decreasing solar heating shutting down outgassing, the increasing distance spreading the already faint light across larger detector areas. Spectroscopy captures a snapshot, a moment in the comet's journey, representative perhaps of its current state but revealing little about what came before or what will come after. The chemistry frozen in the comet's nucleus accumulated over timescales of millions of years in its birth system, then remained essentially unchanged during millions more years drifting through interstellar space, and now reveals itself during a few months of solar heating before freezing again for the endless journey ahead. The molecules themselves remain stable across these vast timescales: water molecules, carbon monoxide molecules, cyanogen precursors patient and unchanging until energy arrives to release them. The nucleus itself remains unresolved in images, appearing as a point source even in observations from the Hubble Space Telescope, at distances exceeding 1 astronomical unit. A 1 kilometer object subtends an angle far too small for direct imaging, even with the most powerful telescopes. The comet's size must be inferred indirectly, through brightness measurements combined with assumptions about surface reflectivity and the ratio of nucleus to coma contributions. Photometric observations track the comet's brightness over time, measuring how much sunlight reflects from the nucleus and scatters from the dust coma. These measurements span multiple wavelengths, from ultraviolet through visible into infrared, building a picture of how the comet reflects and emits radiation across the spectrum. The brightness varies systematically with distance from the Sun, following inverse square relationships that account for both illumination intensity and observational geometry. The nucleus diameter estimates settle around 0.4 to 1.0 kilometers, with the uncertainty reflecting assumptions about albedo, the fraction of incident sunlight that reflects from the surface. Dark surfaces absorb more light, appearing dimmer and thus seeming smaller when brightness translates to size. Bright surfaces reflect more efficiently, appearing larger for the same intrinsic dimensions. Cometary nuclei typically show very dark surfaces, with albedos around 4%, similar to fresh asphalt. Applying this assumption to 2I Borisov's brightness yields diameters near 1 kilometre, only required careful calibration of brightness measurements across multiple observatories to establish consistent photometry, only needed models relating brightness to size through assumptions about surface properties, only took statistical comparison with solar system comets of known size to validate the methodology. The universe permits size estimation but withholds direct measurement at these distances. Rotation becomes detectable through periodic brightness variations. As the nucleus spins, different surface regions rotate into view, presenting varying cross-sections to both solar illumination and Earth-directed observation. If the nucleus is elongated or has regions of different albedo, the brightness oscillates with the rotation period. Observations of 2I Borisov show subtle variations suggesting a rotation period somewhere between 6 and 12 hours. Though the signal remains weak and the period ambiguous, this rotation rate resembles typical solar system comets, which show rotation periods ranging from a few hours to several days. The rotation carries angular momentum acquired during formation, when countless small collisions imparted net spin to the growing nucleus. Over billions of years, outgassing can alter rotation rates through rocket-like forces as jets of sublimating gas push asymmetrically on the nucleus. But during its long interstellar journey, 2I Borisov experienced no outgassing, its rotation rate presumably stable and unchanged since ejection from its birth system. The mass remains completely unconstrained by observations. No spacecraft flew close enough to measure gravitational deflection. No companion objects orbit the nucleus to reveal its mass through Kepler's laws. Density must be assumed. Typically taken as roughly 400 to 600 kilograms per cubic meter, based on solar system comet measurements and theoretical models of ice dust mixtures with high porosity. Combining assumed density with estimated volume yields, mass estimates around 100 million to 500 million kilograms substantial in human terms, but negligible on planetary scales. Outgassing rates provide additional constraints on nucleus properties. The measured production of water and carbon monoxide implies that a certain fraction of the nucleus surface actively sublimates. If only 10% of the surface contributes to outgassing, a typical value for solar system comets, where most surface remains covered by inactive dust mantles, then the active area and production rate together constrain surface temperature and ice exposure. These calculations generally support the estimated nucleus size and rotation period, providing consistency checks across multiple observational methods. The coma extends several tens of thousands of kilometers from the nucleus at perihelion, visible in detailed images as a fuzzy envelope gradually fading into the background. This coma consists of gas molecules and dust particles lifted from the nucleus by sublimation, expanding outward at velocities around 1 kilometer per second, fast enough to escape the nucleus's weak gravity, but slow compared to orbital velocities. The expanding material follows ballistic trajectories in the Sun's gravitational field, gradually dispersing as the distance from the nucleus increases. Dust tails form as radiation pressure from sunlight pushes dust particles away from the Sun. Larger particles, less affected by radiation pressure, curve along orbital paths closer to the nucleus trajectory. Smaller particles accelerate more efficiently, streaming nearly radially away from the Sun in the classic comet tail geometry. 2I Borisov develops a modest dust tail, visible in images as a faint streak extending anti-sunward. The signature of active cometary outgassing under solar heating only occurred because the comet passed close enough to the Sun for temperatures to drive sublimation. Only required solar radiation pressure to organize ejected dust into visible tail structures. only took Earth-based observers monitoring the right regions of sky with sufficient sensitivity to capture these faint features. The universe creates these displays continuously around countless stars, most never witnessed, most occurring in darkness where no instruments gather light. Some observations suggest subtle changes in brightness that might indicate surface changes, perhaps the breakup of fragile surface layers under thermal stress, or the exposure of fresh ice as dust mantles erode away. These changes remain difficult to confirm, requiring comparison of observations from different times and different observatories with careful attention to photometric calibration and observing geometry. Apparent variations might reflect real nucleus changes, or might simply represent instrumental uncertainties and atmospheric effects. The surface temperature calculations indicate maximum values around 180 to 200 Kelvin near perihelion, cold enough that water ice sublimates slowly but not explosively. Carbon monoxide, volatile even at these low temperatures, drives much of the early activity as the comet approaches. Water production increases closer to perihelion, where temperatures rise sufficiently for efficient water sublimation. The temperature gradient across the nucleus surface creates zones of different activity, sun-facing regions warm and active, shadow regions cold and quiet. Thermal models suggest the subsurface remains colder than the surface, with heat conducting inward only slowly through porous ice-dust mixtures that insulate more than they transmit. Below perhaps half a metre depth, the interior remains at temperatures barely affected by solar heating, preserving the primordial cold from interstellar space or from the comet's formation environment billions of years earlier. This interior ice, if it could be sampled, would reveal the most pristine chemistry, unchanged since the comet's birth. The comet sheds perhaps a few meters of surface material during its passage through the inner solar system, a tiny fraction of its total radius. This mass loss comes from the most active regions, where sublimation proceeds efficiently and where dust mantles remain thin enough that gas can escape. Most of the nucleus surface likely remains covered by thick dust layers that sublimation deposited during previous stellar encounters, insulating the underlying ice and preventing significant activity except in localized active areas. Only a spacecraft flyby could resolve these details definitively, imaging the nucleus at resolutions fine enough to see individual surface features, measuring temperature distributions across the surface, sampling the coma composition directly with mass spectrometers, perhaps even landing to collect samples from the surface. But 2I Borisov's trajectory and discovery timing made such a mission impossible. The comet was discovered too late for any existing spacecraft to alter course for interception, and its hyperbolic trajectory offers no second chance. The opportunity passed, leaving only the remote observations captured during its brief visibility. Hubble Space Telescope observations in late 2019 detect subtle morphological changes in the comet's inner coma. Images captured in mid-December, near perihelion, show slight asymmetries and brightness variations not present in earlier observations. These changes suggest possible nucleus fragmentation, the breakup of a portion of the comet's surface, or the separation of smaller fragments from the main body. Such fragmentations occur commonly in solar system comets, as thermal stress fractures weaken structures, and tidal forces exploit pre-existing faults. The evidence remains ambiguous. The brightness increases slightly, as expected if additional surface area becomes exposed through fragmentation. The coma morphology shows enhanced activity in certain directions, suggesting localized outbursts or the activation of previously dormant regions, but no discrete fragments appear in images with sufficient clarity to confirm actual breakup. The changes might represent surface slumping, the collapse of overhanging cliffs or the exposure of fresh ice as dust mantles fail, rather than complete fragmentation into separate bodies. Thermal stress provides the most likely mechanism. As the comet approaches the Sun, its surface heats unevenly. Sunlit regions warm rapidly, while shadowed areas remain cold. This temperature gradient creates mechanical stress in the nucleus material, particularly if the structure contains pre-existing cracks or weaknesses. Ice sublimates from sun-facing surfaces, removing material and undermining adjacent structures. Eventually something gives way, a cliff collapses, a fractured region separates, fresh ice becomes exposed. Solar system comets fragment regularly, sometimes spectacularly. Observations document numerous cases of comets splitting into multiple pieces, occasionally disintegrating completely into clouds of debris. The fragmentation of comet Shoemaker-Levy 9 before its collision with Jupiter in 1994 demonstrated how tidal stress could tear a comet apart. More recently, Comet 73P Schwarzmann-Wachmann 3 broke into dozens of fragments during its 2006 apparition, creating a spectacular display as the pieces separated and developed individual comae. Only required 2I Borisov to approach within 2 astronomical units of the Sun for thermal stress to become significant. Only needed the nucleus to contain structural weaknesses from its formation or from impact damage during its long journey. Only took careful observation during the perihelion passage to detect the subtle brightness and morphology changes that might indicate fragmentation. The universe tests cometary structures repeatedly, breaking the weak and preserving the strong through natural selection on geological timescales. The potential fragmentation raises questions about the comet's structural integrity. Did the nucleus hold together as a single coherent body throughout its interstellar journey? Or did it consist of loosely bound components that began separating under solar heating? Cometary nuclei often resemble gravitational aggregates, rubble piles held together by their own weak gravity rather than material strength. Such structures fragment easily when external forces exceed the minimal binding energy. If fragmentation occurred, the separated pieces would follow slightly different trajectories, gradually diverging as they move away from perihelion. Over weeks or months, the fragments would spread along the orbit, each developing its own coma and tail, each fading independently as distance from the Sun increases. Subsequent observations might have detected these fragments as separate entities, but by late January 2020 the comet had faded sufficiently that detailed morphological studies became impossible with available telescopes. Alternative explanations exist for the observed changes. Perhaps a particularly volatile rich region became exposed, driving enhanced outgassing without actual fragmentation. Perhaps subsurface cavities collapsed, suddenly releasing trapped gas in an outburst event. Perhaps rotation brought differently active regions into view, changing the apparent brightness and coma morphology without any structural change. Distinguishing these possibilities requires higher resolution observations than Hubble could provide at the comet's distance. The fragmentation question matters for understanding interstellar object populations. If interstellar comets fragment easily during stellar encounters, then only the most structurally robust bodies survive long journeys through the galaxy. Fragmentation during passage through a stellar system would populate that system with debris, contributing to zodiacal dust and possibly to meteor streams. But fragments produced during such passages would typically remain bound to the star, captured by gravity, no longer continuing the interstellar journey. Some theoretical models suggest that interstellar comets should be more fragile than typical solar system comets, having experienced fewer close stellar passages and thus retaining pristine, unprocessed structures from their formation. Counter-arguments suggest that only robust objects survive ejection in the first place, that the violent gravitational encounters required to achieve interstellar velocities would shatter weak structures, naturally selecting for strength. 2I Borisov's possible fragmentation provides one data point in this debate, though the ambiguous nature of the observations prevents definitive conclusions. The brightness evolution through perihelion generally matches theoretical predictions for a comet of estimated size undergoing typical sublimation. The slight excess brightness, if real and if caused by fragmentation, represents perhaps a 10 to 20% enhancement noticeable, but not dramatic. This modest increase suggests that any fragmentation remained limited, affecting only a small fraction of the total nucleus mass. Most of the comet survived perihelion intact, continuing outward as a coherent body. Only Hubble possesses sufficient resolution and sensitivity to detect these subtle changes at the comet's distance. Ground-based telescopes, limited by atmospheric turbulence and sky brightness, struggle to resolve morphological details in the inner coma where fragmentation signatures would appear. Space-based observations from above Earth's atmosphere avoid these limitations, providing the stable, high-resolution imaging necessary for detailed morphological studies. The observations required careful planning and execution. Hubble's schedule fills years in advance with competing requests from astronomers worldwide. Targets of opportunity like 2I Borisov receive priority based on scientific importance and time sensitivity. The observations must occur when both the comet and Hubble's orbit align appropriately, when solar elongation permits tracking without interference, when guide stars exist in the field for precision pointing. These constraints limit observation windows to brief periods when all conditions simultaneously satisfy requirements. The data reduction and analysis take months, comparing images from different dates, calibrating brightness measurements, modelling coma morphology, searching for anomalies that might indicate fragmentation or other unusual behaviour. Each image contains noise, random fluctuations in detector counts, cosmic ray hits, background stars, zodiacal light. Extracting real signals from this noise requires sophisticated processing and statistical analysis, applying algorithms that enhance genuine features while suppressing artifacts. Only the most skilled observers and analysts can reliably detect subtle brightness variations and morphological asymmetries in these challenging datasets. Only careful comparison with theoretical models can distinguish fragmentation signatures from normal cometary activity. Only publication in peer-reviewed journals, where other experts critique the analysis and interpretation, provides confidence that the conclusions represent genuine insights rather than instrumental artifacts or processing errors. The universe presents evidence but requires human expertise to interpret that evidence correctly. The comet continues moving regardless of whether fragmentation occurred, regardless of whether humans noticed, regardless of the debates and uncertainties. It carries whatever structure it possesses intact or fragmenting, strong or weak outward from the sun, back toward the cold where sublimation ceases and observation becomes impossible. The questions about its integrity may never receive definitive answers, remaining as ambiguities in the historical record of interstellar object studies. The dust-to-gas ratio settles near unity through multiple measurement techniques, indicating that 2I Borisov ejects comparable masses of dust particles and gas molecules. This ratio resembles values observed in typical solar system comets, where sublimating ice drags entrain dust grains out of the nucleus matrix. The similarity suggests similar internal structures, porous ice-dust mixtures with dust grains embedded throughout the icy matrix, rather than concentrated in distinct layers or regions. Colour measurements reveal reddish hues in both the nucleus and dust, with spectral slopes indicating enhanced reflectivity at longer wavelengths. This reddish coloration characterises most cometary surfaces, caused by complex organic molecules called tholins that form when ultraviolet radiation and cosmic rays process simple ices over geological timescales. Methane, ammonia, and other volatiles exposed to radiation polymerize into long carbon chains and aromatic compounds that absorb blue light preferentially, leaving the red wavelengths to dominate the reflected spectrum. The specific colour indices measured for 2I Borisov fall within the range observed for solar system comets, particularly those from the Oort cloud that represent primitive, minimally processed material. The red colour indicates the comet's surface experienced radiation exposure, either during its interstellar journey or while residing in its birth system's outer regions. Cosmic rays penetrate cometary nuclei to depths of perhaps a metre, processing ice into organic residues even in the absence of stellar radiation. Only required multi-wavelength photometry to establish the colour indices, only needed comparison with well-characterised solar system comets to contextualise the measurements, only took spectroscopic confirmation that the red colour correlates with organic compounds rather than mineral content. The universe paints comets in similar colours regardless of origin. using identical chemistry to produce identical hues. The dust grain sizes remain poorly constrained but likely span a wide distribution from submicron particles up to millimeter-scale fragments. Radiation pressure affects different grain sizes differently. Small grains accelerate rapidly away from the Sun, forming straight tails, while large grains follow curved trajectories that stay closer to the nucleus orbit. Observations show both behaviors, suggesting a continuous size distribution similar to solar system comets, where fragmentation during ejection breaks larger aggregates into smaller pieces. Polarization measurements provide additional information about dust properties. Light scattered by dust grains becomes partially polarized, with the degree of polarization depending on grain size, composition, and structure. Observations of 2I Borisov show polarization characteristics consistent with porous, irregularly shaped grains composed of silicates and organics. These properties match solar system cometary dust, suggesting similar formation processes created similar grain structures in both environments. The dust composition itself cannot be determined directly from the remote observations. Spectroscopic features in the reflected light provide some constraints, suggesting silicate minerals mixed with carbonaceous material. More detailed composition would require spacecraft collection and laboratory analysis, techniques successfully applied to samples from comets Wild 2 and 67P Churyumov-Gerasimenko, but impossible for 2I Borisov given its trajectory and discovery timing. Theoretical models of protoplanetary disk chemistry predict that dust grains form through condensation and coagulation in the cooling gas surrounding young stars. Silicates condense at temperatures around 1400 Kelvin, forming submicron crystals that stick together through van der Waals forces and electrostatic attraction. Organic compounds condense at lower temperatures, coating silicate cores with carbon-rich mantles. Ice mantles accumulate in the coldest regions, binding dust aggregates into larger structures that eventually grow into comets. This formation sequence operates identically whether in the Sun's protoplanetary disk or in disks around other stars. The physics of condensation, the chemistry of carbon and silicon and oxygen, the timescales of coagulation all follow universal principles that produce similar outcomes. The similarity of 2I Borisov's dust properties to solar system values provides observational confirmation of this theoretical universality. Only the dust that escapes the nucleus becomes observable. Most dust remains trapped within the nucleus matrix, bound by ice and never exposed to sublimation. The observable dust represents a biased sample material close enough to active regions that gas drag can lift it, small enough that gravity cannot hold it, resistant enough that it survives ejection without complete fragmentation. This selection effect complicates interpretation, making the observable dust potentially unrepresentative of the nucleus bulk composition. The dust production rate peaks near perihelion, following the water production rate closely. This correlation indicates that water sublimation drives most dust ejection, with expanding water vapor providing the necessary drag forces. Carbon monoxide, despite its high abundance, contributes less to dust ejection because it sublimates at lower temperatures where gas pressures remain too weak to efficiently lift dust grains. Dust jets sometimes appear in high-resolution images of solar system comets, localized streams of enhanced dust emission originating from active vents on the nucleus surface. Such features might exist on 2I Borisov but remain unresolved at the comet's distance. The general coma morphology appears relatively symmetric, suggesting either multiple active regions distributed around the nucleus or a single dominant active region oriented toward Earth and the Sun during observation periods. The dust grains gradually disperse after ejection, pushed by radiation pressure and planetary gravitational perturbations, spreading along and across the orbit. Over timescales of years to centuries, the dust forms a diffuse cloud along the comet's trajectory. For solar system comets, such dust clouds create meteor streams that Earth occasionally traverses, producing meteor showers as dust grains enter the atmosphere. 2I Borisov's dust, however, follows the hyperbolic trajectory back into interstellar space. dispersing too widely for any chance Earth encounter. Only careful photometric monitoring over weeks and months reveals how dust properties evolve with solar distance. Only comparison with detailed models of dust dynamics and radiation pressure effects allows inference of grain properties from brightness and morphology data. Only accumulated experience with solar system comets provides the baseline against which interstellar visitors can be compared. The universe permits comparison but conceals absolute truth behind layers of inference and modeling. The overall dust behavior production rates, colors, polarization, morphology supports the conclusion that 2I Borisov behaves as a typical active comet despite its interstellar origin. This typicality surprises some theorists who expected interstellar comets might show exotic properties distinguishing them from solar system objects. Instead, the observations reveal familiarity, suggesting that comet formation and evolution proceed similarly across different stellar environments, that the basic physics of ice and dust and sublimation transcends individual planetary systems. The trajectory backward through space offers no definitive answer to the question of origin. Astronomers calculate the comet's path through the galaxy, accounting for the sun's motion around the Milky Way's center, for the gravitational influence of nearby stellar associations, for the differential rotation of the galactic disk that shears trajectories over time. The calculations extend back millions of years, tracking the comet's probable path through three-dimensional space as stars drift in their own orbits around the galactic center. No star system within 100 light-years shows a trajectory that intersects the comet's path with sufficient confidence to claim identification as the birth system. Several candidates appear promising stars of appropriate spectral type located roughly along the comet's incoming direction, but the uncertainties in both stellar proper motions and the comet's pre-solar system trajectory remain too large for definitive matching. The comet could have originated from any of dozens or hundreds of systems within that volume of space. The stellar neighborhood changes over millions of years. Stars that are close neighbors today were farther away 1 million years ago. Stars currently distant might have passed within light years of the Sun at some point in the past. The comet's journey through this shifting landscape of gravitational influences follows a path that becomes increasingly uncertain as the calculation extends backward in time. Small uncertainties in velocity compound into large positional uncertainties over mega-year timescales. Only required precise measurements of the comet's velocity and trajectory through the solar system to begin the backward calculation. Only needed accurate catalogues of nearby stellar positions and motions to compare against the comet's path. Only took acknowledgement that uncertainties grow with time to recognize the fundamental limits on origin identification. The universe permits asking where but rarely provides unambiguous answers across galactic distances and timescales. Some candidate parent stars receive particular attention. Kruger 60, a binary red dwarf system currently about 13 light-years away, lies roughly along the comet's incoming direction and has appropriate kinematics for a possible match. But the uncertainties allow for encounter geometries ranging from near collision to tens of light-years separation, making the association plausible but unproven. Other candidates include various FG and K-type stars within 50 light-years, all with trajectories that might intersect the comet's path within uncertainty margins. The problem resembles forensics conducted across immense scales. Given a projectile's current trajectory, reconstruct where it originated. But unlike terrestrial forensics, where ballistics operates in controlled environments over seconds or minutes, this reconstruction spans light-years and millions of years through a gravitational field that shifts as stars orbit the galaxy, with uncertainties in every measurement parameter. The evidence exists but admits multiple interpretations. Statistical approaches suggest the comet most likely originated from a star system 100 to 300 light-years away, ejected perhaps 5 to 10 million years ago based on its current velocity and the typical speeds of stars in the galactic neighborhood. These estimates carry enormous uncertainties. The actual distance could range from 30 to 1,000 light-years, the ejection time from 1 to 50 million years. The statistics provide probable ranges rather than definite values. The comet's velocity relative to the local standard of rest, approximately 32 km per second, falls within typical values for stars in the solar neighbourhood. This velocity indicates the comet was not ejected at extreme speeds by some catastrophic event, but rather departed its birth system through more gentle processes like planetary migration or stellar flyby encounters. Such processes impart velocities of tens of kilometers per second, sufficient for escape but not dramatically exceeding escape velocity. Galactic orbital calculations place the comet on a path that keeps it within the galactic disk, never venturing far above or below the plane where most stars congregate. This orbital geometry increases the probability of occasional encounters with stellar systems during its journey. Though most passages likely occurred at distances of light years rather than the tens of astronomical units where gravitational capture might occur, the galaxy contains vast emptiness between stars, and the comet passed through that emptiness for most of its journey. The radiation environment during interstellar transit remains relatively benign. Cosmic rays penetrate the nucleus, processing surface and near-surface ices into organic residues. Starlight diffuse and distant rather than focused and intense provides minimal heating, keeping the comet's interior at temperatures near 10 to 20 Kelvin, cold enough that even volatile species like carbon monoxide remain frozen. Interstellar dust grains impact the nucleus at high velocities, eroding the surface at rates of perhaps micrometers per million years, negligible compared to the nucleus size. Only the comet itself experienced the journey. Only its structure records the impacts, the radiation exposure, the long cold passage through near-perfect vacuum. Only its chemistry preserves whatever signatures might distinguish interstellar transit from residence in a planetary system's Oort cloud, but detecting those signatures requires measurements beyond what remote observation permits, requiring sampling and laboratory analysis that the comet's trajectory makes impossible. Some researchers suggest that interstellar comets might accumulate mantles of processed organic material during their journeys, cosmic ray irradiation converting surface ices into complex tholins that insulate the interior. Others argue that erosion from interstellar dust impacts continually remove such mantles, exposing fresh ice and maintaining a relatively pristine surface. Observations of 2I Borisov cannot distinguish these scenarios. Both predict reddish colours and organic spectral signatures consistent with what telescopes detected. The question of origin matters for understanding planetary system architecture and evolution. If the comet originated from a system with different planet configurations than the solar system, its composition might reveal how planet positions influence comet chemistry. If it came from a system around a cooler star, the high carbon monoxide abundance might trace directly to lower disk temperatures. But without identifying the parent system, these connections remain speculative, possible interpretations rather than proven conclusions. Future surveys may detect enough interstellar objects to perform statistical analyses correlating compositions with incoming directions, searching for common origins, identifying stellar associations that produce distinctive chemical signatures. With dozens or hundreds of well-characterized interstellar visitors, patterns might emerge that reveal systematic differences between comets from different stellar populations. 2I Borisov represents the second data point in a dataset that eventually might grow large enough for such analyses. The comet continues its journey, carrying its origin as an unanswered question. Whatever star system gave it birth continues evolving, its planets orbiting, its remaining comets waiting in cold storage, unaware that one of their siblings travels through another stellar system light years away. The birth system and the visitor proceed through separate futures, connected only by history that neither can record or remember. Ejection from a planetary system requires specific dynamical conditions, gravitational interactions energetic enough to unbind objects from their parent star while not destroying them completely. Planetary migration provides the most commonly invoked mechanism, gas giant planets forming in the outer disk and spiraling inward through interactions with remaining gas and planetesimals, their shifting orbits scattering nearby smaller bodies. Some scatter inward toward the star, others outward to establish new distant orbits, and some achieve velocities exceeding escape velocity, departing the system entirely. The early solar system experienced such migration. Jupiter and Saturn likely formed farther from the Sun than their current positions, migrating inward during the gas disk phase before reversing and moving outward as the disk dissipated. This migration scattered planetesimals throughout the system, some inward to bombard the terrestrial planets, others outward to populate the Kuiper belt and Oort cloud. A fraction achieved escape velocity, becoming the Sun's contribution to the interstellar comet population drifting through the galaxy. Numerical simulations of planetary system formation suggest that ejection efficiency varies with planet masses and orbital configurations. Systems with multiple massive planets in compact orbits eject more material than systems with fewer or less massive giants. Systems where planets undergo significant migration eject material at different velocity distributions than systems where planets remain near their formation locations. The ejection process selects for specific orbital starting conditions. Objects on certain orbits preferentially receive the gravitational kicks needed for escape. Only required solving Newton's equations for thousands of test particles interacting with migrating planets to establish ejection statistics. Only needed computational power sufficient to integrate orbits over millions of time steps as planets slowly change position. Only took decades of planetary formation research to develop the theoretical framework connecting observations to physical processes. The universe operates through gravity that humans can calculate but still struggle to predict in complex multi-body systems. Stellar encounters provide an alternative ejection mechanism. Binary star systems, where two stars orbit each other, create time-varying gravitational fields that efficiently perturb distant comets. A stellar flyby, another star passing within a light-year or less of the target system, similarly disturbs weakly bound outer system objects. The perturbed comets find their orbits altered, some falling into the inner system, others gaining energy and escaping to interstellar space. The Sun likely experienced several close stellar encounters during its 4.6 billion year lifetime. Passage through dense stellar regions like the spiral arms increases encounter frequency. The current stellar neighbourhood shows relatively low density, but the Sun's galactic orbit periodically brings it through denser regions where close encounters become more probable. Each encounter sends objects from the solar system into interstellar space while potentially capturing objects from the passing star system. The ejection velocity distribution depends on encounter geometry and stellar masses. Close encounters impart higher velocities. Encounters with massive stars transfer more energy than encounters with low-mass stars. The distribution of ejection velocities determines how far ejected objects travel and how frequently they encounter other stellar systems. Objects ejected at high velocities traverse larger galactic volumes but spend less time near any particular star. Objects ejected at low velocities remain in the general neighbourhood of their birth system, potentially re-encountering it millions of years later. Statistical models based on these ejection mechanisms predict that the interstellar medium contains vast numbers of ejected comets, asteroids, and planetesimals. Estimates suggest that every star system contributes billions to trillions of objects to the interstellar population during its formation and early evolution. Multiplied across billions of stars in the galaxy, the total population becomes truly astronomical, perhaps 10^24 interstellar objects, larger than 1 meter diameter drifting through the Milky Way. Most of these objects remain forever dark and frozen, never again approaching a star closely enough to become active or observable. A tiny fraction passes through stellar systems like ours, and an even tinier fraction of those transits occurs during a time when technological civilizations have developed instruments capable of detection. The detection of 2 interstellar objects in 3 years suggests Earth's instruments have finally achieved sufficient sensitivity to begin sampling this vast hidden population. Only chance determines which objects transit which systems. Only probability governs whether transits occur during epochs when observers exist. Only the most recent few decades of human technological development provided the telescopic and computational capabilities necessary for interstellar object identification. Before that, such objects certainly transited through the solar system but passed unnoticed, their interstellar nature unrecognized, their presence recorded at best as anonymous comets or not recorded at all. The ejection process imparts no memory to the ejected objects. They carry composition and structure determined by formation conditions, but they receive no special marker identifying which system ejected them or when ejection occurred. The chemistry provides clues to formation environment, but chemistry alone cannot uniquely identify a source system. Millions of stars form similar planets producing similar comets with similar compositions. Some ejection scenarios predict that planets themselves might be ejected, particularly lower mass planets like super-Earths or mini-Neptunes that form in large numbers in some systems. These rogue planets would drift through the galaxy, potentially maintaining internal heat from radioactive decay and residual formation energy, possibly even retaining atmospheres sustained by pressure rather than proximity to a star. Such worlds remain hypothetical, predicted by simulations but not yet definitively detected. The efficiency of ejection varies over a planetary system's lifetime. Early phases when planets migrate actively and many planetesimals remain available show high ejection rates. Later phases when planet orbits stabilize and most small bodies have been cleared show much lower rates. Most ejection probably occurs within the first 100 million years of a system's existence. During the chaotic period before stable configurations emerge, T.I. Borisov likely experienced ejection during its birth system's youth. Launched into interstellar space when that system's planets underwent migration and settling, it carried the chemical signature of formation in the outer system where volatiles remained abundant, where temperatures permitted carbon monoxide ice to condense, where radiation from the young star had not yet processed all the primordial ices into more complex compounds. Then it drifted, cold and dark, for millions of years until chance brought it through this solar system, briefly visible before continuing its endless journey. Only one star system provided the specific gravitational environment that ejected this particular comet at this particular velocity in this particular direction. Only one sequence of planetary encounters imparted the exact momentum that set it on a course eventually intersecting the solar system. Only one birth environment produced its distinctive chemistry, but that star system remains anonymous, one among billions, identifiable in principle, but not in practice given current observational capabilities and the vast uncertainties involved in backward trajectory integration. The observational window closes gradually as the comet recedes from perihelion, moving outward through the solar system on its hyperbolic escape trajectory. Solar distance increases, reducing both the sunlight available for reflection and the heating that drives out gassing. The comet dims according to inverse square relationships, brightness falling with the square of increasing distance. Spectroscopy becomes impossible first, requiring signal strengths that fade below detection thresholds by February 2020. Photometry continues somewhat longer, tracking overall brightness even as spectral details disappear into noise. By March 2020, the comet has passed Jupiter's orbit outward bound, approximately 5 astronomical units from the Sun. At this distance, the surface temperature has dropped to perhaps 120 Kelvin, cold enough that water sublimation essentially ceases. Carbon monoxide continues outgassing weakly, maintaining a tenuous coma, but the activity declines rapidly as available solar energy diminishes. The comet begins its transition back to the dormant frozen state it maintained throughout its interstellar journey. Hubble attempts final observations in March, pushing detection limits to capture images of the fading coma. The observations succeed marginally, showing the comet as a faint smudge barely distinguishable from background noise. These final images provide closure to the observation campaign, documenting the comet's appearance at the edge of detectability before it fades completely beyond even Hubble's capabilities. The observation span from discovery in August 2019 through final detection in March 2020, 7 months of active monitoring, capturing the comet's perihelion passage and initial outbound journey. Only the most sensitive instruments could follow the comet through its entire observable passage. Only coordinated campaigns involving multiple observatories worldwide could accumulate sufficient data for comprehensive analysis. Only rapid response to the discovery allowed observations to begin early enough to capture pre-perihelion behavior. The universe provides brief windows of opportunity that require preparation and capability to exploit effectively. Ground-based observatories contribute observations throughout the visibility period, their larger collecting areas compensating somewhat for atmospheric interference. The Gemini telescopes in Hawaii and Chile, the Very Large Telescope in Chile, the Keck telescopes in Hawaii. These major facilities dedicate time to 2I Borisov observations, adding to the growing dataset. Each observatory provides complementary capabilities, different instruments optimized for different measurements, together building a more complete picture than any single facility could provide alone. Amateur astronomers also contribute observations, particularly brightness measurements that track the comet's light curve over time. These observations require less sophisticated equipment than spectroscopy, but provide valuable temporal coverage, filling gaps between professional observations. The tradition of amateur comet observation extends back centuries, and 2I Borisov benefits from this tradition despite its exotic origin. Comets remain one of the few astronomical phenomena where amateur contributions meaningfully advance scientific understanding. Radio observations attempt to detect molecular emission lines at millimeter wavelengths, seeking species like carbon monoxide and hydrogen cyanide that emit efficiently in the radio spectrum. The Atacama Large Millimeter Array in Chile, with its exceptional sensitivity and angular resolution, observes the comet multiple times. These observations confirm carbon monoxide emission and provide independent measurements of production rates, validating optical and infrared spectroscopy results through completely different detection methods. Infrared observations from space-based telescopes like Spitzer provide additional spectroscopic data before that telescope's retirement. Infrared wavelengths reveal thermal emission from dust grains and detect molecular bands that appear weakly or not at all in optical spectra. The infrared data complement optical observations, constraining dust properties and detecting molecular species present at lower abundances. Each wavelength regime offers unique information, together creating a multi-wavelength portrait of the comet's composition and behavior. The accumulation of data from multiple observatories and multiple wavelength regimes allows cross-validation of results. When different instruments using different techniques measure the same parameters, production rates, nucleus size, dust properties, the consistency of results provides confidence that measurements reflect real properties rather than instrumental artifacts. Discrepancies between measurements highlight uncertainties and drive refinement of techniques and models. Only 14 months separate discovery from final detection. A brief interval in astronomical terms but sufficient for comprehensive characterization. Only the comet's favourable geometry approaching perihelion shortly after discovery permitted such thorough study. Earlier discovery would have allowed longer observation baselines. Later discovery might have missed perihelion entirely, capturing only the outbound fading phase. The timing proved optimal for extracting maximum scientific value from the observation opportunity. Data analysis continues long after observations cease, as researchers mine the data sets for additional information, refine models, compare results across instruments and techniques. Papers appear in scientific journals throughout 2020 and 2021, each presenting specific analyses, spectroscopic composition, nucleus properties, dynamical origin, comparison with solar system comets. The publication record grows into dozens of papers, each contributing pieces to the overall understanding of this interstellar visitor. Some questions remain unanswered even after analysis concludes. The exact nucleus size remains uncertain within factor of 2 margins. The rotation period shows ambiguity. Whether fragmentation actually occurred stays debatable. The parent star system eludes identification. These uncertainties persist not from lack of effort, but from fundamental limitations. The comet remained too distant for certain measurements. too faint for required signal-to-noise ratios, observable too briefly for long-term monitoring that might resolve ambiguities. The final consensus describes Borisov as a comet remarkably similar to solar system comets in most measurable properties, with composition and behaviour falling within the ranges observed locally despite its extrasolar origin. The elevated carbon monoxide abundance stands as the primary distinction, suggesting formation in colder conditions than typical solar system comets, but not radically different conditions. The universality of comet properties across stellar systems emerges as the key scientific conclusion. Planet formation produces similar outcomes regardless of specific stellar parameters, at least within the range of conditions sampled by this single example. Only one interstellar comet has been thoroughly characterized as of Borisov's passage. Oumuamua, detected earlier, provided too little data for detailed comparison. Future interstellar objects will undoubtedly appear as survey capabilities improve, perhaps revealing greater diversity than these first two examples suggest. Borisov establishes a baseline for comparison, the first well-characterized interstellar comet against which future discoveries can be measured. Its properties define expectations that future objects will either confirm or challenge. The comet itself moves beyond observability, crossing into regions where sunlight spreads too thin for meaningful measurements, where even reflected light from Earth's largest telescopes cannot reach across the widening distance to capture return signals. The scientific campaign concludes not with dramatic finale, but with gradual fading, observations becoming sparser and less certain, until finally no telescope can distinguish comet from background, and the effort ends quietly. The first interstellar object detected, Oumuamua, appeared in October 2017, tumbling through the inner solar system on a hyperbolic trajectory that immediately suggested extrasolar origin. That object provided mostly frustration to astronomers. It showed no cometary activity, no coma, no tail, no spectroscopic signatures of outgassing. It appeared as a point source in all images, revealing nothing about surface composition or structure. Its unusual elongated shape, inferred from large brightness variations as it rotated, sparked speculation about artificial origin that media amplified beyond scientific reasonableness. The lack of activity made Oumuamua difficult to classify. Without outgassing, it resembled an asteroid more than a comet, suggesting rocky or metallic composition, but some observations hinted at subtle acceleration beyond what gravity alone could explain, as if weak outgassing too faint for detection provided small but measurable thrust. This ambiguity frustrated attempts at definitive characterization. The object might be a dormant comet with a thick dust mantle preventing activity, or a fragment of a destroyed larger body, or something genuinely unusual in composition or structure. Oumuamua was discovered only after perihelion passage, already receding from the Sun when telescopes first identified it. The discovery came too late for comprehensive observation campaigns. Within weeks of detection, the object had faded beyond spectroscopic capability. Within months, it became too faint for any further observations. The brief window captured only limited data trajectory, rotation period, brightness variations, color measurements insufficient for the detailed characterization that scientists desired. Only Oumuamua's unusual trajectory prompted the careful analysis that revealed its interstellar nature. Only dedicated observers tracking near-Earth asteroids provided the detection that made any observations possible. Only rapid recognition of its significance triggered the brief observational campaign that captured what limited data exists. The universe offered a glimpse that humans barely managed to perceive before the object faded into permanent obscurity. Borisov arrived differently. Detected before perihelion while still approaching the Sun, the comet provided months of advance warning. Astronomers could plan observation campaigns, schedule telescope time, coordinate multi-wavelength studies. The comet showed obvious activity from discovery onward, outgassing visibly, developing a coma and tail, behaving in every observable way like typical solar system comets. This familiarity made it easier to study, to compare with existing knowledge, to place within understood frameworks of cometary science. The contrast between the two objects illustrates sampling bias and observational selection effects. Oumuamua's lack of activity made it difficult to detect only its close passage to Earth, brought it within detection limits. Thousands of similar inactive objects might pass through the solar system undetected, too dark to reveal themselves against the stellar background. Active comets like 2I Borisov appear brighter due to their coma, extending detectability to greater distances and improving discovery probability. This detection bias complicates population statistics. The ratio of detected comets to detected asteroids among interstellar objects might not reflect the true population ratio. If most interstellar objects resemble Oumuamua rather than 2I Borisov dormant and dark, then the true population vastly exceeds the detected population, with only the occasional active comet revealing itself through outgassing. Alternatively, if most objects resemble 2I Borisov, then the population might be smaller than extreme estimates suggest, with detection efficiency higher for the typical object. The behavioral differences raise questions about interstellar object diversity. Do both cometary and asteroidal bodies populate the interstellar medium in comparable numbers? Do compositional differences reflect formation in different regions of parent stellar systems? Ice-rich bodies from outer regions and rocky bodies from inner regions? Do activity differences result from compositional variation or from surface processing during long interstellar transits that suppress outgassing through dust mantle accumulation? Only additional detections can answer these questions statistically. Only samples large enough to show population distributions can reveal whether Oumuamua or 2I Borisov better represents the typical interstellar object. Only systematic surveys capable of detecting both active and inactive bodies can establish true population ratios unbiased by observational selection effects. Current data comprising two objects permits only speculation about underlying populations. Oumuamua's mysterious acceleration remains unexplained, but probably traces to weak outgassing below detection thresholds. Even minimal gas production, invisible to spectroscopy, generates sufficient thrust to produce the observed trajectory deviations. The outgassing need not involve water. More volatile species like carbon monoxide or nitrogen could sublimate even at the large solar distances where Oumuamua showed non-gravitational acceleration. This interpretation requires no exotic physics, only cometary behavior scaled to faint levels. 2I Borisov showed no comparable acceleration anomalies. Its trajectory matched gravitational predictions within measurement uncertainties. Either its outgassing occurred symmetrically enough that thrust forces cancelled, or the comet's larger size and more vigorous activity made thrust effects negligible compared to total momentum. The absence of detectable non-gravitational forces simplified orbital calculations, but provided less information about outgassing asymmetries and rotation outgassing couplings. The two objects together establish that interstellar visitors show diversity in properties and behavior. They arrive with different compositions, different activity levels, different trajectories. They demand different observational approaches and yield different types of information. Generalizing from two examples risks oversimplification, but the contrast demonstrates that no single interstellar object should define expectations for all future discoveries. Only time and improved survey capabilities will reveal how common interstellar visitors truly are, how diverse their properties, how representative these first detections of the larger population. The Large Synoptic Survey Telescope, now operational and renamed the Vera-C Rubin Observatory, should detect dozens of interstellar objects per year once it reaches full survey cadence. This flood of detections will transform the field from case studies of individual objects into statistical population analyses. Future observations may detect interstellar comets showing activity levels far exceeding 2I Borisov, or objects with compositions dramatically different from anything in the solar system, or artifacts of planetary collision not obviously cometary or asteroidal in nature. The diversity might prove limited, with most objects resembling either Oumuamua or 2I Borisov, or it might prove extensive, with each detection revealing new variations. The data will decide, not speculation. 2I Borisov's predictable behaviour, outgassing, fading, following expected trajectories provided reassurance that interstellar comets obey familiar physics. After Oumuamua's puzzling properties sparked debates and exotic hypotheses, 2I Borisov returned the discussion to conventional comet science. It demonstrated that the first interstellar object detected was unusual, not that interstellar objects generally are unusual. Most interstellar comets probably resemble 2I Borisov more than Oumuamua, active and comprehensible within existing frameworks. Statistical models of interstellar object populations begin with assumptions about ejection rates from planetary systems. Each star system, during its formation and early evolution, scatters some fraction of its planetesimals into interstellar space through planetary migration and stellar encounters. The ejection efficiency depends on system architecture, number of planets, their masses, orbital configurations, timing of migration. Systems with massive planets eject more material. Systems undergoing substantial migration eject material over longer timescales. Estimates suggest that typical planetary systems might eject 10 to 100 Earth masses of material over their lifetimes, mostly during the first 100 million years but continuing at lower rates thereafter. This ejected material fragments into individual objects ranging from dust grains to dwarf planet-sized bodies. The size distribution probably follows power laws similar to those observed in solar system small body populations, with many small objects for each large one. Multiplying ejection rates by the number of stars in the galaxy yields total population estimates. The Milky Way contains approximately 100 billion stars. If each star system ejects even modest amounts of material, the accumulated population of interstellar objects becomes enormous, perhaps 10 to 24 objects larger than 1 meter across, 10 to 15 objects larger than 1 kilometer, millions of objects larger than Pluto. These objects drift through the galaxy, filling the space between stars with invisible debris from planetary formation. Only a tiny fraction of these objects ever passes close enough to a star to become potentially observable. The galaxy spans roughly 100,000 light-years in diameter, but contains only 100 billion stars, implying that most volume consists of empty interstellar space. An object ejected from one stellar system might drift for billions of years without ever approaching another star closely. When encounters do occur, they typically involve passage at distances of light-years, close enough to slightly perturb trajectories through gravitational interaction, but far too distant for the objects to become visible. The solar system's cross-section for interstellar object transits depends on how transit is defined. If defined as passage within Neptune's orbit, roughly 30 astronomical units, then the cross-section spans about 3 × 10⁹ of the sky, as seen from typical interstellar distances. Most interstellar objects passing through the Sun's general neighbourhood miss this target entirely, their trajectories carrying them past at distances where solar gravity produces negligible deflection, and where no Earth-based telescope could detect them. Statistical calculations accounting for the solar system's motion through the galaxy, the velocity distribution of interstellar objects, and detection capabilities suggest that objects larger than 100 meters should pass through the inner solar system, within a few astronomical units of the Sun, at rates of several per year. Objects larger than 1 kilometer pass through at rates of several per decade. These rates match observed detection frequencies remarkably well, given that systematic sky surveys capable of detecting such objects began operating only in the last few years. Only recently have survey telescopes achieved sufficient sky coverage, revisit frequency, and sensitivity to reliably detect interstellar visitors. The Pan-STARRS survey in Hawaii, which discovered Oumuamua, began operations in 2010. The Catalina Sky Survey, Atlas, and other programs ramped up capabilities throughout the 2010s. Before these surveys, interstellar objects transiting the solar system would have been missed entirely or detected but not recognized as interstellar due to insufficient orbital coverage. The detection rate should increase as survey capabilities improve. The Vera-C Rubin Observatory, with its 4-meter primary mirror and wide-field camera, will image the entire visible sky every few nights, detecting moving objects down to much fainter magnitudes than previous surveys. Projections suggest it might detect dozens to hundreds of interstellar objects annually once operating at full capacity. This detection rate will quickly build sample sizes sufficient for population statistics. With larger samples, patterns may emerge. Perhaps certain compositions correlate with incoming directions, suggesting contributions from specific stellar populations in the galaxy. Perhaps activity levels vary systematically, indicating different surface processing histories. Perhaps size distributions show structures reflecting planet formation processes in the parent systems. Perhaps none of these patterns appear, indicating thorough mixing of ejected populations during their long galactic journeys. The size distribution of detected objects will remain biased toward larger bodies for decades. Small objects meter-scale or smaller transit through the solar system constantly, but remain too faint for detection, except in rare cases where they pass extremely close to Earth. Even Rubin Observatory will struggle to detect kilometre-scale objects at distances beyond a few astronomical units. The detected population will overrepresent large objects, requiring statistical corrections to infer true size distributions. Some fraction of interstellar objects might show activity unlike anything observed in solar system comets. Exotic ice compositions, methane-dominated or nitrogen-dominated, or containing species unknown in solar system bodies might produce unusual outgassing patterns or colours. Alternatively, the population might prove monotonously similar, with every interstellar comet resembling solar system comets as closely as 2I Borisov does, confirming universality but disappointing those hoping for exotic chemistry. The frequency of transits through the solar system implies that Earth's atmosphere encounters interstellar dust regularly. Small particles from fragmented comets or from dust directly ejected during planet formation enter the atmosphere constantly, burning up as meteors. These particles carry interstellar compositions but arrive individually, unassociated with parent bodies, making their interstellar origin difficult to prove. Occasionally, larger fragments might survive atmospheric entry, delivering interstellar material to Earth's surface among the thousands of tons of meteoritic material that accumulate annually. Only isotopic analysis of meteorites might reveal interstellar origins, if the isotopic ratios differ sufficiently from solar system values, but most interstellar objects probably formed from gas clouds with compositions similar to the Sun's parent cloud, making isotopic discrimination difficult. Identifying an interstellar meteorite among the vast collection of solar system meteorites remains challenging without contextual evidence like observed atmospheric entry linked to known interstellar object passages. The statistical population models remain speculative, constrained by limited data. The detection of 2 interstellar objects in 3 years provides one data point: the detection rate. Everything else, size distributions, composition frequencies, diversity of properties, awaits future observations. Theory predicts, but the universe decides what actually exists and what properties those objects carry. The galaxy steadily converts planetary system material into interstellar populations through ongoing ejection processes. New stars form continuously, their planetary systems ejecting material. Old systems continue ejecting through stellar encounters and long-term dynamical evolution. The interstellar object population grows slowly over galactic history, accumulating the debris of billions of planetary systems across billions of years, filling the space between stars with frozen archives of planet formation. The similarities between 2I Borisov and solar system comets suggest that planet formation follows similar pathways across different stellar environments: water ice, carbon monoxide, cyanogen precursors, organic dust. These components appear in both interstellar and solar system comets, indicating that the chemistry of protoplanetary disks operates identically, regardless of which star provides central illumination. The fundamental physics of gas cooling, dust condensation, ice formation, and planetesimal growth transcends individual circumstances. Protoplanetary disks form when interstellar gas clouds collapse under their own gravity. Conservation of angular momentum spinning the infalling material into rotating disks around nascent stars. Temperatures in these disks decrease with distance from the central star, creating chemical gradients as different species condense at different radial distances. Close to the star, only refractory materials like silicates and metals remain solid. Farther out, water ice condenses. Still farther, more volatile ices like carbon monoxide and methane become stable. These chemical gradients operate in every protoplanetary disk, governed by the balance between stellar heating and radiative cooling. A hotter star pushes the ice lines farther outward, a cooler star brings them closer in, but the sequence remains the same: refractory, water ice. Volatile ices producing similar compositional structures across different systems. Planets and planetesimals forming at similar temperatures relative to their ice lines develop similar compositions regardless of absolute distances or stellar properties. Only the universal nature of physics and chemistry permits such similarity. Only the fact that hydrogen, oxygen, carbon, and nitrogen behave identically everywhere allows different stellar systems to produce comparable outcomes. Only the reproducibility of thermodynamic processes ensures that cooling gas clouds follow similar evolution, whether collapsing 4.6 billion years ago in the Sun's formation region, or collapsing around some other star at some other time. The universe uses the same recipe everywhere, varying ingredients proportions but following identical preparation instructions. The convergence towards similar outcomes emerges naturally from the limited options available to collapsing gas clouds. Hydrogen dominates cosmic abundances, with helium second and heavier elements present only as traces. The heavy elements combine into molecules determined by chemical affinity, and temperature water forms readily from abundant oxygen and hydrogen. Carbon monoxide combines carbon with remaining oxygen. Nitrogen forms ammonia, or nitrogen-bearing organics. The same elements following the same chemistry inevitably produce similar molecular inventories. Dust grains demonstrate similar universality. Silicates and carbonaceous materials dominate solid particles in protoplanetary disks, formed from condensation of silicon, magnesium, iron, carbon, and oxygen. These grains grow through collisions and electrostatic attraction, forming aggregates that eventually grow into planetesimals. The process operates identically in different disks because the physics of particle collisions and the chemistry of grain formation follow universal principles, independent of stellar parameters beyond temperature profiles. The timescales of planet formation might vary between systems' massive disks forming planets faster, low-mass disks taking longer, but the end products show remarkable similarity. Rocky planets form in warm inner regions. Ice giants form beyond snow lines where volatiles condense. Gas giants form where solid surface density permits rapid core growth before gas disk dissipates. The architecture repeats with variations in details but consistency in broad structure. Observations of exoplanetary systems confirm this general pattern. Hot Jupiter's gas giants orbiting extremely close to their stars demonstrate that planet migration occurs commonly, though migration distances and timescales vary. Super-Earths, rare in the solar system but common elsewhere, show that small planet formation proceeds efficiently in many environments. The diversity of observed systems reflects variations in initial conditions and evolutionary paths, but underlying processes remain universal. Borisov's chemistry fits naturally into this universal framework. Its high carbon monoxide abundance indicates formation beyond the CO ice line, in a disk cold enough for carbon monoxide condensation. Its water content indicates formation in an environment where water ice existed abundantly. Its organic dust indicates radiation processing of simple ices over long time scales. None of these properties requires special circumstances. They emerge naturally from standard planet formation processes operating under typical conditions. The universality extends to dynamical processes. Planetary migration occurs through disk interactions and planet-planet scattering. Mechanisms that operate identically regardless of stellar mass or system architecture. Ejection occurs through gravitational encounters following Newtonian mechanics that applies everywhere. The scattering and ejection that produced interstellar objects like 2I Borisov operate continuously in planetary systems throughout the galaxy, following identical physical laws. Only the details vary between systems. One system might form 5 gas giants, another only 2. One disk might contain twice the solid material of another. One system might experience more violent migration, another relatively gentle evolution. But these variations occur within a framework of universal processes, like variations on a theme rather than entirely different compositions. The theme gravity, thermodynamics, chemistry, collision physics plays out reliably everywhere. This universality carries profound implications for the prevalence of habitable environments. If planet formation follows similar pathways across stellar systems, producing similar chemical inventories and similar planetary architectures, then the conditions that led to life on Earth probably exist elsewhere. Water, organic molecules, energy sources, stable planetary surfaces, these prerequisites for life as understood, emerge naturally from standard planet formation. They represent typical outcomes rather than unlikely coincidences. The search for biosignatures in exoplanet atmospheres assumes such universality. If atmospheric chemistry operated entirely differently in other systems, Earth-based intuitions about what biosignatures to seek would fail. But if atmospheric chemistry follows universal principles, oxygen production from photosynthesis, methane production from biological decay, chemical disequilibria maintained by life, then detecting these signatures in exoplanet spectra might actually indicate biological activity rather than exotic abiotic chemistry. 2I Borisov's journey brings news from another system, a chemical message stating that planet formation there followed recognizable patterns. The comet carries no artificial information, no encoded data, no intentional communication, but its composition communicates nonetheless, speaking through molecular ratios and isotopic abundances, through dust properties and outgassing behavior, through every measurable parameter that reflects its origin. The message reads, the universe operates consistently, following the same rules here and there, then and now. Only one interstellar comet well characterized so far, yet that single example suggests universality. Only limited data, yet that data points toward fundamental similarities rather than dramatic differences. Only the beginning of interstellar object studies, yet already patterns emerge suggesting that planetary systems, despite their diversity, share common formation mechanisms and chemical pathways. The universe reveals its consistency through the wanderers it sends between stars. The comet moves beyond Neptune's orbit now, more than 30 astronomical units from the Sun, farther than the distance where most sunlight fades into the general stellar background. The surface temperature has dropped below 100 Kelvin, cold enough that all outgassing ceases. Water remains frozen solid. Even carbon monoxide, the most volatile component detected, no longer sublimates at significant rates. The comet returns to the dormant frozen state it maintained throughout its interstellar journey. Its brief period of activity concluded, its temporary visibility ended. Solar gravity still influences the trajectory, but weakens with increasing distance. At Neptune's orbit, the Sun's gravitational acceleration measures about 1/10,000th of Earth's surface gravity. Weak, but sufficient to curve trajectories noticeably. Beyond a few hundred astronomical units, solar gravity becomes comparable to gravitational perturbations from passing stars and the collective influence of the galactic disk. The comet transitions from the Sun's domain back to the galaxy's domain, no longer primarily a solar system object but an interstellar traveller temporarily visiting. The velocity relative to the Sun continues increasing as the hyperbolic trajectory converts gravitational potential energy into kinetic energy. The comet arrived at approximately 32 km per second and will depart faster, carrying the additional velocity gained falling toward perihelion and climbing back out. Eventually, thousands of years hence, it will cross the heliopause, the boundary where solar wind surrenders to interstellar medium at roughly 34 km per second, slightly faster than arrival velocity. Only gravity accelerates it. Only the mathematical inevitability of hyperbolic trajectories determines the exit velocity. Only conservation of energy ensures that the comet gains speed proportional to how deeply it fell into the Sun's gravitational well. The universe permits no exceptions to conservation laws, no special provisions for objects that arrive from elsewhere, no privileged trajectories that escape the mathematics of orbital mechanics. Beyond the heliopause lies the Oort cloud, a spherical shell of comets extending perhaps 100,000 astronomical units from the Sun halfway to the nearest stars. 2I Borisov will pass through this region over the next several thousand years, moving through a sparse population of frozen objects that belong to the solar system, but orbit so distantly that stellar perturbations influence them as much as solar gravity. The comet will not interact with these objects, space remains too vast. Collision probability is too low, but it shares the darkness with them temporarily during its outbound passage. The nearby stars toward which the comet travels include several candidates within 50 light-years. At 34 km per second, the comet covers 1 light-year in approximately 800 years. Reaching stars 50 light-years distant requires roughly 440,000 years of travel. The comet departed its birth system perhaps 5 to 10 million years ago, suggesting it has already travelled hundreds of light-years. The journey ahead spans timescales longer than human civilizations, longer than most species' existence, approaching the timescales of geological epochs and evolutionary transitions. During this journey, the comet experiences near total darkness and cold. The Sun fades to just another star. No brighter than Sirius or Canopus appear from Earth, providing negligible heating. Starlight from all directions contributes diffuse illumination, insufficient to drive photochemistry or raise temperatures above the cosmic microwave background. The comet's surface temperature stabilizes around 10 to 20 Kelvin, determined by the balance between absorbed starlight and thermal radiation into space. Cosmic rays continue bombarding the nucleus. High-energy particles from supernovae and other energetic sources scattered throughout the galaxy. These particles penetrate meters into the ice, breaking molecular bonds, creating free radicals, driving slow chemical evolution even in the absence of heat. Over millions of years, this radiation processing converts simple ices into complex organic molecules, creating the reddish tholins that colour cometary surfaces. The chemistry proceeds slowly but continuously, accumulating changes that eventually alter surface properties. Interstellar dust grains impact the nucleus at velocities of tens of kilometers per second, each impact releasing enough energy to vaporize small amounts of surface material. The impact rate remains low, perhaps 1 grain per square meter per million years, for micron-sized particles, but accumulates over geological timescales. The erosion removes perhaps micrometers of surface per million years, negligible compared to the kilometer-scale nucleus diameter, but sufficient to slowly refresh the surface, exposing new material and removing the most heavily processed outer layers. The comet carries no record of its journey, no memory of the observations it received, no awareness of the attention it briefly attracted. It moves according to gravity and momentum, indifferent to significance or meaning, following the trajectory that previous gravitational encounters determined. Whatever happens in the solar system after its departure, new discoveries, technological advances, the rise or fall of civilizations occurs without the comet's participation or knowledge. Occasionally the comet might pass within light years of another stellar system, experiencing gravitational deflection that alters its trajectory slightly. More rarely, It might pass close enough to a star for that star's gravity to significantly change its velocity and direction, potentially even capturing it into a long-period orbit. Such capture events occur with extremely low probability, perhaps one chance in thousands over millions of years, but given sufficient time, even unlikely events eventually occur. If captured by another star, the comet would repeat its passage through that system's inner regions, warming and outgassing if it approaches closely enough, perhaps being observed by astronomers in that system if technological civilizations happen to exist there and then, or it might simply orbit quietly in that system's outer reaches, indistinguishable from native comets except through detailed compositional analysis that might reveal subtle chemical differences. Its interstellar journey would end, though whether such ending constitutes arrival or mere cessation of travel remains a question of perspective. More likely, the comet continues drifting indefinitely, passing between stars without close encounters, moving through the galaxy's spiral arms and interarm regions, slowly orbiting the galactic center, along with billions of stars and trillions of other ejected objects. Its journey has no destination, no purpose, no conclusion beyond eventual impact or tidal disruption in some future encounter impossible to predict from current trajectory data. The chemistry frozen in its nucleus preserves information about its birth system, the temperature at which its ice condensed, the radiation environment during formation, the elemental abundances in its parent star's protoplanetary disk. This information persists across millions of years and light-years of distance, encoded in molecular ratios and isotopic compositions, readable by any sufficiently advanced civilization that intercepts the comet. 2I Borisov carried such information through the solar system, revealing it briefly to human instruments before continuing onward with its archive intact. Only chance brought it through the solar system during an epoch when humans possessed instruments capable of detection and analysis. Only timing placed it on a trajectory visible from Earth during the brief window of human technological civilization. Only probability, nothing more, determined that this particular comet among countless interstellar wanderers would be detected, studied, characterized, and remembered in scientific literature. The universe arranges no meetings, ensures no observations, guarantees nothing except that physics will be obeyed and probabilities will eventually manifest. The comet moves outward through darkness toward other darknesses, carrying its secrets and its memories of formation under another star. It maintains its cold, patient trajectory, changing only as gravity requires, neither hastening nor delaying, simply existing and moving through the vast spaces between stars where most of the galaxy's volume resides empty and dark and silent. The darkness accepts the comet back into itself. The brief interval of visibility concluded, the temporary warmth fading into cold that will last for epochs unmeasured and perhaps unmeasurable. Somewhere ahead in the vast geometry of the galaxy, stars continue their slow orbits around the galactic center, their light spreading outward into space, most of it travelling forever without encountering anything capable of appreciating its passage. The comet moves through this light, reflects infinitesimal fractions of it, absorbs photons that contribute negligibly to its temperature, and continues. Time becomes meaningless at these scales. 1,000,000 years passes as indistinguishably as a single year. The comet experiences no change, maintains no awareness of duration, simply persists in its frozen state, while the galaxy rotates slowly beneath it. Stars that were young when the comet began its journey might die before it completes another stellar encounter. Stars not yet born might form, age, and fade during its continued drift through the interstellar medium. The ice remains stable at these temperatures, molecules locked in crystal structures that will persist essentially forever unless disturbed by impact or stellar heating. Water molecules, carbon monoxide molecules, dust grains embedded in the matrix, all frozen into configurations that change only on quantum timescales, through tunneling effects and rare molecular rearrangements that accumulate over billions of years into barely measurable alterations. Perhaps other comets drift nearby, separated by light years but sharing the same vast emptiness, each carrying chemistry from different stellar systems, each moving on its own trajectory through the galaxy's gravitational field. They will never meet, never interact, never even detect each other's presence. The galaxy remains too large, its volume too vast, for such encounters except across timescales longer than the universe's current age. The silence is complete. No atmosphere carries sound. No magnetic field channels particles into aurora. No tectonic activity stirs the frozen interior. The comet exists in a state of such profound stillness that Earth's quietest desert at midnight would seem tumultuous by comparison. It is the silence of deep space, of the void between stars, where nothing happens and nothing will happen for longer than minds can comfortably contemplate. And yet the chemistry persists, the structure endures, the trajectory continues. The comet remains real, remains physical, remains subject to natural laws that operate without attention or observation. It carries forward through time and space the information encoded at its formation, a frozen archive drifting through the galaxy, waiting for nothing, expected by nothing, simply being and moving as the mathematics of gravity and momentum require. The story has no ending because the journey has no conclusion, only continuation into futures that stretch beyond prediction. The universe permits such journeys, accommodates such wanderers, makes space for frozen archives that drift between stars carrying news that may never be received. The comet moves onward. The darkness remains. Time passes at its inexorable rate, and somewhere far behind, instruments that briefly tracked its passage turn to observe other objects while the data gradually archives into memory storage, preserved as ones and zeros, as permanent as human records ever become, which is to say, temporarily, which is to say long enough, sleep, then rest in the knowledge that the universe continues its slow evolution, that comets drift through darkness, that ice remains frozen in the deep cold between stars, that gravity binds and momentum carries, and time progresses whether observed or not. The journey continues without witnesses, the cold persists without complaint, the silence holds without breaking. All is as it should be, all is as it must be, all simply is.